Hello.
Hello.
Hi, everybody. Let me. I wonder. Okay, so I think I accidentally stopped the music at some point. I'm sorry. I'm not sure when I did that, but apparently I did stop the music at some point. Anyway, so
Hi.
hello, Anka. Right, so let's see. What was the button? Okay, that's the button. Teach me math.
Yay!
Okay, cool. So what's the plan for today? Well, it's
Hi.
help me. Not pointing at you, pointing past you.
Ah.
There's the plan for today.
Okay.
It's like floating in the air
Like
here.
This.
Right.
Hi.
Hey, Bolt. Hello. Right. So the plan is we'll do the parser interpreter for STLCs, for some version of STLC. It's not literally like the first version, right?
No.
Is it the first? Like literally, they just start off with some types and
but with
products
some-
and no, we're adding some types and
We
products,
adding
right?
sometimes some and products.
Some and products, just to
Mhm.
be slightly more interesting, right? So we'll try writing the parser, the interpreter, and then we'll see if we have more time. We might start into. So it's simply type lambda calculus. You can use the let me run it. So it's like it will be a trivial programming language, right? Where you can only do you can have some types, product types, and functions.
Function types. And you can define your
And you can define types, right?
Right. But maybe we should say what's the main goal of this experiment.
Right,
What
so
we plan to do.
Okay, so that's step one, right?
Okay.
Step one is to just do this. Then
Yeah.
step two is to kind of the goal of
The goal,
step
yeah.
two is a longer step, but the ultimate goal of step two is to have some sort of proof deduct. How do you call it? Like
No, we want to
generate implementations. is
generate
the,
all implementation generate implementation for
given a type.
given a type, right?
Right, which is kind of like in logic, this is called proof search, right? If we
Yes.
go through the Curry-Howard correspondence.
Yes, and what we want to do is we want to use a special secant calculus for intuitionistic logic, minimal logic. This means intuitionistic logic without bottom, right? Without false.
Mhm.
In order to get all the proofs. Well, to get a proof for a
In order to get
to check
roughly like a minimally efficient algorithm,
Yes.
because otherwise you can just search right through the whole universe and you'll find them
I
probably.
hope you'll not be dead by the time it will finish.
But it's
Yeah.
like there's actually no real algorithm. You just write for
You
natural
have to,
deduction.
You have to guess. Yeah,
You have to
that's-
guess. So
Okay, so let's stay focused. So what we want to do is use a secant calculus in order to find proof, or to say that there is no proof. We will also be able to say this, and then translate this proof in natural deduction, and then from that go back to our simply type lambda calculus in order to give an.
so we're a couple of level dips there.
Yes,
Levels dip.
How you say?
Type theory.
Yeah, we will do this.
Yeah, maybe
okay.
we'll start it today, but I'm not sure.
Okay, the main takeaway for the moment is that, maybe you know Curry-Howard isomorphism, which is the connection between simply type lambda calculus and natural deduction. Okay, so, but secant calculus is another formalism for intuitionistic logic, in which you can, which has better algorithmic properties. Like with natural deduction, you cannot write an algorithm which will say, okay, you can prove this theorem, right? Because we will go into more details. But for example, with modus ponens, right? You have to guess some formulas, so there is some magic there. But with secant calculus, it just goes straight forward. Well, with a special kind of secant calculus.
I mean,
So
yeah.
we will be able to implement.
But we'll explain when we get there, right? It's the galaxy brain.
Okay.
So no, I mean we'll explain. It's actually a lot simpler than it sounds.
Yeah, it sounds complicated, but it's actually.
It's just like some syntax we need to get used to, and then we're done, right? That's
Yep.
pretty much it.
Yeah.
It's just like the sequence.
Well, we have to see how. I'm looking forward to for Vlad to show me how we will encode the proof, because they look like trees.
You have to show me that.
I don't know. We will see. We will figure it
I
out.
can do the monkey coding. You need to explain the algorithm.
We will.
So anyway, let's write some code, right? Because that's why we're here.
Okay, and we have books.
We have books, yeah.
We have books, and we also have books for
Math books.
math books, but I'm sorry, they're reversed.
Anyway,
Anyway,
so let's see. I guess let's just create like some.
okay, we're gonna do it.
So should we start with like the syntax tree, like the type?
Yeah.
We'll just create some syntax. Like some syntax module.
Mhm.
And now I guess it's you
Okay,
tell
so
us
the idea is we somehow follow
the
the
tuple.
book, the tuple book, but maybe we will rename some of the constructors,
Mhm.
and yeah.
So do we want to not have any primitives and just allow user like okay, so one thing is we don't want numbers yet because that will complicate everything.
Yeah, but we want, for example, to be able to say, okay, I have type A or B or C, right? Because also when we move to logic, we need to have like propositional variables.
So we need type declarations.
Mhm.
Yeah, we need type declarations.
Yeah.
So do we start with that?
Okay.
Okay. So I mean, yeah, I have no idea what I'm doing. I've never done this before, so let's think, right? So we need a type declaration, right?
Not related.
The book name is not related to the tuple. What do you mean?
No, it's like
Oh no, it's types and programming languages.
Sorry, like Pierce. Big book.
It's like the so if you're into like if you want to learn type theory, that's the like book if you're looking at it from a computer science perspective.
Yeah.
And there's different books if you're more interested in the like proof theory part of type theory
Or from mathematical.
or mathematics, but this
Yeah.
is like the computer scientist's handbook for type theory pretty much. It shows you how to implement all of these different lambda calculi in camel or something
I
like
think
that.
it's ML.
Or ML, yeah, some ML. Whatever.
Okay.
Okay, so we have a type, right? So what does a type have? Well, I'm not typing in the right window. So a type would have something like I guess it can be new type. It has a name for sure, right?
Mm-hmm.
Do we want type names to be different than other names, or do we just define like, okay, we have some, like what other names do we have? We have type names, we have constructor names, function names, right? Variable names probably if we want to allow binding. Do we like
Yep.
do we treat them similarly? Are they all names? I guess so, right? Because you want to look up things and you want to kind of be in the same spot, right? So so maybe we have a new name, right? Just to differentiate from regular strings, right? We just give it a different name. So okay, so we can have a name. The type has a name, and I guess do we encode them as sums of products? That's the usual encoding for constructors in languages like Haskell or PureScript.
I would keep it as so. I'm just thinking from the on our next steps in which we will move to logic and how we want to bring back the proof from logic, and for that we will need to have like the simple types without using type constructors. So you just need the names, right? And then because if you have a type A and you have two types A and B, right? And then I will be able to speak about the formula A and formula B, which will be the smallest blocks.
So we can only define aliases? Like, okay, so we cannot introduce new constructor names, is what you're saying? Or we can?
I think no.
So let's start without that?
Let's start without that.
Okay, but then
you will be able to refer to the type A plus B, right? The sum. But then that will be a formula. I think it will help us to make a difference between smaller blocks.
Let me
and
write some
then-
pseudo syntax for our language,
Okay, yeah.
just to make sure. So let's see, like maybe we can write it somewhere in test, because we're probably going to be using this if we want to write tests, right? So let's say
Should we be making a
types,
class?
making a class. I don't think so. Hello, Yu-Gi-Oh, welcome.
Hi.
So let's do LC, our like lambda calculus, or right. So maybe you're saying we can do this type A, right, and type B, and then you can do maybe A plus B, right?
Yes, exactly.
Something like this. But like,
And that will be a type
that's
as well.
okay. And then A,
But it's like a component.
and this is a construct product, right?
Yeah.
And then okay, so maybe we could do something like this. Sorry, true and false, and you can define true plus false as booleans, maybe, right?
Okay.
Like that's the encoding of booleans in like literally.
Yeah. Okay.
Okay. So do you want to? Okay. So then we don't even think about allowing some like alias boolean equals to,
No.
right? We will do that later. If,
Yeah. Let's just keep it as simple as possible.
So not this. Just you can just define this
Yeah.
sort of thing.
Hey.
And now you get to see the cool new.
Hey.
Welcome,
Hi.
Cassie. Whoa! I finally managed to upload that thing on somewhere and to set up my OBS. So I need to. I don't think that works. I don't think that works, unfortunately. I think if you unfollow and refollow, you don't see that. But I can show it again.
Okay, do it again.
I can trigger it manually.
Ooh.
Yeah. Okay, so this is what you're trying to encode. Okay, cool. So then the syntax is just a name, right? It's a
Yeah.
type with a name, and that's all we care about, right? Okay, so then we can. I guess we can just do this, right? If it only has one property, we don't need to name
Okay.
it necessarily, right? Oh wait, but it's a name, right? It's a doubly, right? Do we want this or let's just do string then?
Yeah.
We don't need this.
Okay.
Okay, so those are the types, right? We can define. Well, we don't have a tree yet, right? So let's do data AST, let's call it, right, for the syntax tree.
Okay.
And then let's say. So what are the options? Well, one option is a type declaration, right? Where the only thing we care about is the type, right? Because it's a
Okay.
string, so that's how we write it. Are you going to use recursion schemes? Yes.
Okay. Okay.
No, yeah. Okay, so we now have an AST with type declarations. What else do we need?
Okay, then we will have function types.
Function types. Okay, so function types are. I'm totally not biased because I'm writing my LC to use recursion schemes right now. I love recursion schemes, so I think we'll use it. Actually, before this, I literally included the recursion schemes library here. So, oops. So let's go back. Right, so functions. How do we define functions? Because this is a bit tricky, right? So let's see.
Yes, exactly.
That was premeditated.
This was while I was putting the baby for a nap, so this is what he did.
So let's see, data function, right? So function can either be like, is A a function or only A to be a function?
A.
Like is A the generate type of function? I think that it should be, right?
I think we need that.
So it's kind of like like we need two names.
Okay.
Like how do you call the terminator? Result, right? Because that's the end result, and then we can have like argument, which takes a type and a function, right? That's how it works. I'm not crazy, right?
Argument?
Yeah, because you go like argue or input. Does input sound better? That's cool. Terminator equals R. Right, because you can do terminator argument A, argument B, result C, right? And this is kind of A to B to C.
And you want to write argument A, argument B instead of A to B to C?
No, like we need a type, right? We can
Okay.
have like this. This is not a parser. This is
Okay.
just the syntax tree, right?
Okay.
And like, yeah. How is a function? What do you mean a union?
Like a sum.
It's a list, right? Like ultimately, it's a list. So it
Yeah.
looks like a list. It's a list of types.
Just leave what you wrote before as a comment.
What do you mean? Oh, you mean this?
Yeah.
Okay. Well, this is literally a list. Like this is exactly equivalent to list of types, right? This is, well, not really. It's a non-empty list.
Mhm.
It's a non-empty list because you're forced to have one argument.
Mhm.
Yeah.
Just leave the example.
Oops.
That would be.
Right. This is the result. Although I think this is this is right? Because like this is how we
But
think about
can we
functions,
say-
right? Right? Because that's like this is how we see functions in
Instead
LC.
of argument and result, maybe should we use like target and source?
I mean that sounds very like FRP-ish. That's like functional reactive programming or something. Just make
Okay.
function type. Well, it has to be type if it's type, then it's you can only allow like regular. Well, okay, you can then make functions to be also types. It's kind of like some mutual recursion between function and types here, which makes things a bit hairier. Right now, the result can be function as well. Here, it can't be. This has to be a
It has
string
to
right
be a
now.
string.
So we're not allowing that right now. So this is kind of like the functions have to, the result has to be normalized in a way.
Mhm.
I don't think, right? Because then here we'll just do like, but like this isn't a function declaration. This is a function type declaration, right?
Mhm.
But we also need its body, like the implementation.
Mhm.
So that's the like, so there's no point in. Okay.
There was a question like, the type function should be array type?
Yeah, I mentioned that. I think it's more non-empty array because we have this.
Mhm.
Because it doesn't make sense to have nothing, right? It has to be non-empty. So we could use like data non-empty. Although I much prefer list than array. Non-empty list. I guess we could say over type. I guess it's the same thing. Sorry, it's function over this. So are we intentionally forbidding higher order functions? No, we're not. Let me think. So should we actually allow that? And how should we do that? So I think we can do this instead then, but then how do we terminate it?
But
Well, no, I think the result. Although, okay, I get the problem is this. I think, right? Is that the problem? Are we good now? Yeah, that also might be a good idea. But I think this also solves it. Okay, let's explore the other idea. So otherwise, we could do a type. Okay, and I misspelled this. Okay, we could also do this, where we have a type could be just a a simple type, or I don't even know, just a type, right, with a name. Or it could be a function, right? It could be a function like from a type to a different type, right? And then we can have all different possibilities here, right? Because that can be simple types, or any of these can also be function, right? And yeah, let's just do this for now. And then we can also encode sum and products here, and then that's what all the types are. I think I like that better actually. Yeah, and then we can have like sum between two types, and then we can have product between two types, right?
Yeah.
And then this is a lot better. Yeah. Yeah, I think that was Yu-Gi-Oh's idea. Good idea. That seems much better. Yep. Okay, so then a type declaration is a type. Yep, that's cool. So we can have type declarations. Although, wait, no. So this is different because a type declaration should be just this thing, right? So, okay, so type declaration needs to be something like type A, right?
Right.
So this needs to be just a. Oh wait, we have two instances of type here. This is a type name. Or something like that.
You had one misspelled.
I think that was the problem. I think that's the problem. Right, so this is for type A, and then this is for... okay, so... like, okay, what's the other syntax? I think I should take a type and an AST, right? No, I think this is just a type signature. Okay, so then we have something like this. Like, do we want to write something like F and then of type A?
Yep.
Okay, so that's like the declaration, and then we have a definition, right? So maybe I guess the next thing we need is a term. Oh, thank you. Oh, I have no idea how to read your name, but thank you very much for the follow. Hello. Right, so we have a term definition, term def, I guess.
Okay.
Or which has to be both, right? It's that plus f equals to something, right?
Okay.
So this needs a type, right? Well, okay, it needs a. Okay, let's rename type name to symbol.
Okay.
Right? And then maybe we'll also use symbol here for type names. What do you mean for one stream one? No, this is for like it's it's not for this stream. It's the channel's new animation. It's not just for this stream. Okay, just you saying. Okay, so this is the only. Okay, I get it. I misread. Okay, so we have like a symbol, which is the F,
Okay.
right? Type, which is this, right? Well, and here you could obviously have A plus B times C, whatever, right? Okay, and then we need like the term. Oh, and thank you very much for the follow, New Swim.
Hello.
Oh wait, no, that's a sub. Okay, sorry. Thank you very much for the subscription, New Swim. Sorry, I'm not used to the new animations, so I don't even know what I'm looking
you have
at.
Like a color.
Yeah, it's just the color is different. Oh, thank you very much for watching and subscribing.
Hi.
No, it's the same animation. Like my brother spent quite a bit of time working. Yeah, it's a different color. Yeah. Anyway, so okay, so we need some sort of like how do we? What's this? It's like the implementation, right? It's like the term, I guess, which one should call it, right? Yeah, body.
It's the term. No, just
term.
keep
Yeah,
term.
I guess.
Or inhabitant. It is the inhabitant, right?
Right. So let's see. Yeah. So let's see. Okay. So how like what can we do? What can we do here inside the term? Okay, so I guess we need to look here, right? So if we have functions, we need to be able to do like lambda abstraction. Like we need to bind parameters. I'm not sure how
so
is
you
that.
need like lambda.
Yeah, lambda x, whatever, right?
Let's
use the other cool new feature that we have. Okay. Are you ready?
Yeah.
There we go. Oop. Wait, why is it not showing? Okay, we're currently experiencing technical difficulties.
For the elevator
you need
music.
to you need to insert the thing there. Okay. It's We'll start. Okay, give me 1 second, because this is the thing. You need to, yeah.
Good.
Yeah, you need to go back to the other window now.
Mhm.
So I guess if it goes in like standby, it closes.
No problem.
Okay. Chats, don't look. You've seen nothing. Okay, so let's see. If I do this, does it work now? Okay. Just 1 tiny second.
We will have
Okay,
to do
there
this
we
every
go.
time.
Hopefully not. Okay.
Okay.
So let's see. Does it work now? There we go.
Hi.
Technology. Let me move. You don't need to see this here, right? I can just do this.
Okay, so we want to have something like, let's see, lambda x, right?
Too many woes for one stream.
Right.
Well, I guess what we would like to be able to write here. Okay, so let's start writing the term, right? So first thing we would like to do is be able to do something like lambda x, and then we can use dot or like arrow, whatever we feel like.
Not arrow, dot.
Dot, okay, right? So then we can do this or whatever, like things like this, right? So.
Well, I would write x, y, blah blah, right? Until the dot.
Like this. That could be syntax sugar, but
Yeah.
then the term should probably be the thing that like the sugar thing. Then we
Okay,
can do this
okay.
at parsing or a
Okay,
different
okay.
sort of step, right? I'm not sure. So I'm fairly sure that we don't need any type annotations until we introduce complicated things. I don't think we need that.
Okay.
Okay, so we need something like something for this, right? I guess we can add them later, but for now I want to do the simplest thing because yeah, it will. It's not going to be as simple as anyway. So this, what was this called? Is it? I guess it's abstraction, right?
Yep.
It's lambda abstraction. Right? That's the name.
Yeah.
Let's call it abstraction, and then we just need a symbol, right? We just need a name, and we'll use just one now. And then it's a term, of course, right? It's
Okay.
because you have like some term here, right?
Okay.
Were you thinking differently?
Oh no, I think it's good.
Okay, we can have a non-empty list here if you want from the beginning.
Yep.
Should we do that? Should we add a non-empty list here?
Yep.
Okay. Okay, cool. Okay, and then.
Yep.
Yeah, exactly. And like the non-empty list. Okay, so now we've made it so that you can have multiple things here, right? And then the term. Okay, so what other things can we do? Well, we should be able to apply.
Yeah.
Right. So.
Okay.
I mean, let's use the like
Okay.
long names and then, which is kind of like
Like two terms,
fx, right?
Mhm.
Yeah, it's only two terms. Yeah, because
Term,
like
term.
if you have multiple, we'll just so it's term to term, right? That's the like simplest thing. Actually, so do you want to use terms or symbols here? Actually, do you even do? Okay, I guess it's this all the same because this has to also be like symbol.
Yeah, but you need to start with.
So what
You can have
like-
symbol too, right?
how should we call it?
Var or variable.
Okay. So what's the advantage of using a list instead of the sugar version? Oh, there are two ways to write the same thing. I'm not sure what you mean. Oh, you mean this one? I think convenience is the. But yeah, indeed, like now there's more ways. Like, it's not obvious what the like optimal version is or the expected version is. We'll come back here maybe at some point. right? And here it would be, yeah, so you can have two symbols here next to each other, or you can have something more complicated. Okay, so this handles function types, right? We don't need anything to handle function types extra.
No. Okay,
So now we need to handle
further.
sum types, right?
Yep.
So I guess we need three things, right? We need to construct sum types, and we need to two things.
Okay, let's so sometimes. Okay, we call it this either left and right.
Yeah. So we want to be able to do like left x, right? So it's left and then term, right?
Right.
And right term. I think this is for building sum types, right?
Right.
But then, okay, so I guess this means that we kind of need to figure out from the context what's the other. Yeah, exactly. It's just x. Like this is kind of this. We need this in order to be able to say this, for example, right? In an abstraction, because otherwise you can't. If you don't have this, I don't think you can even write a term, right? So
yeah, that's the
terminator for the
the smallest brick.
and then we need to we need maybe, right?
Sorry. Maybe either.
Sorry, either. Yeah, it's right, which is I. So this is kind of like the. Like let me hide this because we don't need it right now.
Okay. Right.
But yeah, Anka, you're right. I think I'll if we ever run into trouble here, I'll change it back to just a symbol. So here we need something quite specific, right? Well, but I guess we can't really do that. So we need like three terms, right? But this normally is something like if we were to type them, we would say that either is something like A to C and then B to, well, okay, first, okay, we can just write right to B, no, B to C, and then you give me an sum of A, B, and I'll give you back a C, right? Yeah, it's the function rather than because like this is what you can use at the term level. Like it's the eliminator for sum types, right? And then we have for product, right? We have like we call it tuple, I guess, right? Which is the constructor. So that's like xy, I guess. Right, and you can create a tuple out of two terms. And then there's the deconstructing of tuples. Well, no, we can get like, we don't need deconstruction, right? We can just do left and right, or like first and second. Right? I mean, we're deliberately naming them with their Haskell names just to make it easier. I think in like the book, they're called different, like in left and in right and things like that.
P1 or P2.
P1 and P2 instead of first and second and stuff like that, right? But I'm deliberately using Haskell / PureScript names because it's easier.
If you want, we can rename.
No, I'm good. And I think that's it.
Yep.
Oh, sorry. I think that's all there is to, well, it's not that simple, but it's all there is to writing a term, right? So I guess that's our whole AST, right? Like the complicated part of the AST is the term, right? Everything else is just.
Yep.
Okay, so now I have to write a parser for this.
Yay.
Okay, let me think, because before we do that, if we want to be able to use, let me have a quick look, because I've used. So I want to have a very, very quick look at Matryoshka, the recursion schemes library. Because in Haskell, you need to do this thing that's a bit awkward for your type. You need to do the like base functor. And I've not used this library in a long time, so I want to have a look whether that sort of awkwardness is required here as well or not. So we have, you don't have to use base. Okay, so I can do a, okay, I care about the recursive rather than co-recursive thing. So where is the recursive? Okay, not co-recursive. Okay, there we go, recursive. Okay. So all you need to do is project, which is from, so what's, yeah, but then you still need, you still kind of need to be able to, okay, since you already have mu f and new f here, you kind of have to define your type in terms of this in order to use it, right? Or at least you need a base functor anyway. So you either end up duplicating code, right? So you either end up writing a second version of term, which is identical but uses term everywhere here. In order to do that, okay, you know what? That might be an interesting, like, let's see how hard it is to do that if you don't even think about it until then. I'm curious. And if it turns out hard, we'll just write it by hand. You just need a fixed point functor. Yeah, but that means that I essentially need to do term A here and then replace all terms here with A. And then do the same here and do the same in AST and then thread that variable around, right? And then define the, like, this would instead be term FA, and so on. Right? Did you want to write something? No. Or okay. Right, so it's either that or and then we define like our type being term, like some mu version of term f. But the thing is, I want to do the parser without thinking about that, and then I wonder how much trouble we'll get into if we do that. I'm curious.
Okay, it's experiment.
Let's do this experiment. Let's do the parser first, not think about it and be like, oh damn, I wish I thought about this, and then see what happens. Okay, so let's look at the parser then. Let's create a parser. Yeah, so I think we'll use this, where is it? Okay, not this one. Yeah, purescript-parsing. Where is it? Published and pursuit. There we go. So we have two options here.
We have a funny.
We have a what?
Do they see the green lines? Okay.
The what?
No, nothing.
Okay. Here's an example from that library. Okay. Oh, for Matryoshka. Okay. I'll keep it open, but for now I'll have a look at parsing. Okay, so we can either use parser combinators, like manually, more or less, or we can use this sort of like token/language part, which is specifically written to be able to write languages. And it has some examples of how you can write, like, for example, this is how, like, Haskell and so on. And I think token is the module where we can do your own thing. Yeah, you still have to, but it's like, it's a lot easier, right? You have to use parser combinators to define the, like, okay. Okay, so let's see. Because I have not used this before, right? So I have to, like, go through it for a second and figure it out. Okay, so create a parser which return the first token in the stream. Okay. Actually, you know what I'm curious about? How, like, can we just look at how the like simple Haskell or PureScript versions are written, and maybe we can start from that as an example. And Haskell style seems like a minimal version, so maybe we can have a look at this. Okay, empty def. Okay, so this gives us a language definition, right? And we can give comments for start and end, comment line, whether we allow nested comments, indentation start. I'm not even sure what this is. Okay, operations. I'm not sure what this. Oh, so this is just a list of operators. Okay. Reserve names, and then whether it's case sensitive. Okay, so let's say we have a language definition like that, because that doesn't seem hard to define for our language, right? So let's say we have such a language definition. What can we do with it? Okay. Make sure that you use constructors. Oh yeah, I know. Using functions. You need to modify the functions. Yeah, maybe. Okay. So make token parser. Okay, so from this thing, like a gen language def, which is what we get from here, we can get a token parser. Okay, so what's the token parser again? It's just a bunch of parsers, right? That are generated automatically using this. Okay. Make token. Okay, gen token parser. Oh, and then you do this, and then you do combinators using this, right? Like, is this the whole idea?
Should we look at the example?
So you have a language definition here, and it's called language. And then you do, okay, so you have this token parser, and then you have, so you're kind of using, for example, for an expression, using parentheses, identifier, and reserved ops, right? Okay, I mean, let's try. Where did we want to start? I guess we can start from here, right? From something like this. Okay. Okay. Okay, so it's also from token. I think this is also from token, but I'm not sure.
Yeah, I think that will help.
Can you make a file of what language is going to look like so we can refer to it? Well, I mean, if I only knew, right? So should we use the same the same style of comments as in Haskell? I think so, right? Because people are used to that. So yeah, let's skip this. Nested comments, sure. Identifier start letter. Okay, so where is this imported from? Letter. I think it's from. Is it here as well? Okay, it is. Okay, so it's also token. So everything is from token. Okay, and then we need to do where OP is. And we'll have a different list of operators, I guess, right? This is an operator, right? Because we'll use this. I guess this, right? For lambdas. Because we're not going to use. No, it's single, but then this needs to be like escaped.
Dot.
Is it okay? Dot, yeah. Plus, right? Because we want to use some types and product types at the type level here. I think that's all. Oh, and then arrow, right? Because we'll use functions for this.
And for okay,
Is there anything else?
I think
I
no.
don't think so, right?
Mhm.
This is all. Okay, so this should compile.
That's it.
Oh, because those are two. Wait, so how do you do, like, oh, does this only work for like single line? Oh, okay, okay. So then you cannot have a like this in your name or what? But wait, so here did they just do? Oh, okay, so they okay, sure. Okay, so okay, and monads. Let's import prelude for that. Import prelude. There we go. And then one off. Where's one off? So parser string. Parser string. That's 5. Okay, so where's empty def? Oh, empty def is here, right? Okay, so we need to import this module. What's it called? Like language. Okay. And then this is from. Let's just do alternative. And then this was also from the language. Wait, where's one off from? It's from string. Oh, okay, we already have it. Okay. I guess we could do, like, for example, couldn't we just do one of these or string this? Couldn't we just do that?
But he said that we could use some combinator for that.
Reserved op. Okay. What does this? Where is it? Because it's not finding it. Here isn't string what I'm looking for. Oh, okay, okay, I get it. It's not a standalone operator. Oh, so this just took. Okay, never mind. I don't think I need it then. I think it's fine. Okay, yeah, because this is only a single character. Okay, so then I guess you can. Yeah, okay. Okay, so given this, where's the parsing? Token. Okay, so there's this example. Okay, this is the thing that we care about. Okay. So I guess we can now start writing. I guess this will be somewhere, and we can rename this to LC def, right, for roundback calculus definition. Right, and then I guess okay. Let's try actually writing all the things that like what Vince said, because I think that's a good idea. Okay, so let's kind of. Okay, so let's use comments now. So now purescript is commented, and then our thing will be the language, right? So okay, this is a type, right? So like types cannot live at the. So we can only have terms, right? And an AST is like one of those terms, right? It's either a type declaration. Okay, no. So actually, I'm speaking crazy. Okay, let's look at AST. There we go. Right, so you can have a type declaration, literally type A. And that's it, right? That's all we can do. Type B, right? Okay. These are all like type declarations. Right, that's all we can do. And then we can do the term definitions, right? So let's do a simple one, right? A is of type.
But do you have this?
We're missing, I think we're missing something, right? We're missing like the value of type A.
Yep. They have it until
But like, I don't think we want one actually. Because like, I don't think I want to be able to write this. I want to be able to write, like, we only want to be able to write combinators, right? We want to write something for this, for example, right? Right, and this would be something like x, right?
Yeah.
And this actually becomes, so let's try to write it in our AST, right? So this is a term def,
But
right?
did we use this?
Well, we said we'll do this.
Okay.
Is that what you were going to say? No, keywords, I haven't used it. You should add keywords to the reserve names. Yeah, I'll do that. Okay, so let's see. And I guess we also need to have this as a reversed operator and things like that. But I don't think we'll allow operators anyway. Right, so we have a term definition. And I won't use parentheses, I'll just use indentation in new lines because it will be easier to read. So it's a term definition with a symbol. So symbol is IDA, right? And then we have a type, which is, okay, so how do we write types? So type is what? Is function from type to type, right? So first of all, is a function from A, right? And let's do this at least, right? So it's not too confusing.
Why did you write the term def?
Because this is the, like, we're
okay.
getting an AST, right? So it's a function from A to, how did we say, result? What was function again? I don't have function here, right?
We don't have type.
Syntax, because I forgot. I always, wait.
No, we change it. We have the function with type.
Oh, right, okay, so it's just type. Okay, so it's function A, type B, right? Because type, like, is this one, the symbol. Okay. And that's sorry, A. From A to A, right? And then we have the term, which term is abstraction, right? And this is a list which only has X in it, right? It's this one. And then it has a term, a subterm, right? We can do it like this, which is what? It's just variable X, right? Looks right to me.
Wait. In the function, shouldn't you have like type A?
No, because like this is the name of the constructor as well.
Yeah, but the function, okay.
So this is only a symbol, right? And we'll check whether you also have a declaration later, right? But basically you have to declare type A and then you can write this thing, right?
But then on the second one, why did you write type A?
Because it's a function from A, which is the okay, right? I think I know what you mean. Do you mean this?
Yeah.
Is that what you meant? Okay, yeah, you're right.
Okay.
Yeah. Abstraction makes the lambda. So this is like abstraction is literally this, right? Kind of this part, right? Where like this is abstraction, then this is the X here, and then what's after this is the variable X, which is here. So let's maybe write something slightly more interesting. Let's write apply. And then I'm too used to Haskell. So then this is an F, and we said we'll allow like it like this, right? FA dot FA. I guess that's all we need to do.
Yep.
So let's see how we do it. And this is the last one I'll do right now, I think. And then we can start writing parsers, the parser. So this is also a term def. I guess we can copy it from here and change it, which is called apply, right? And it's a function from a function, right? Of type A and type B, right? And this is the first argument. Let's maybe do this. I said I'd use indentation when it makes things easier. And then type A, well, it's another function,
Yeah.
right?
It's a function.
Yeah.
Like the one, just copy what we have above.
Okay, yeah, I think that's correct. And then we have an abstraction of X and then, well,
No,
F and then A, right? And then we have application, right? Of variable F and variable X, right? That's all.
Phew.
Okay. What?
Yeah, no.
Okay, so let's start, and I guess we'll figure this one out. Variable A, yeah. Okay, so I guess let's start with a simple thing. Let's parse this type thing. I guess we can add type here just to make sure we don't forget, right? Then we can say something like what type? Well, we can't use type, so let's do the, because type is a reserved keyword in PureScript as well. Parser, I guess. I hate doing this, but whatever. Yeah, I guess probably, yeah.
That's cool.
Okay, so what's this? So we need to make it like a... so what's parser T? It's a monad transformer. Is there's like... Okay, there isn't. I want to see this type though. Because I think we make like... okay, so what's S? S is the stream type, right? So... type parser T, where we use strings as input, and the monad will be what? Identity. Oh, okay. I guess we can use. Okay, so. The string identity.
Maybe you
Yes.
should look more careful.
So I repeat, just in case, you should put your reserved operators in reserved op names array. You look at operator array from the Haskell level. Haskell has custom operators, but we don't have any operators, so I don't think we'll be using this. I can do this, I guess, but I'm not sure if this helps. I mean, I'm not sure if it's needed. But yeah.
Maybe, and also 2 points.
Yeah. Okay, so it's just a parser for. So what does this give us? This gives us a type, right? Yeah. Our own sort of type, and we'll use it here. Okay, so if we want to do this, then I guess we have the keyword type, right? So how do we use, I mean, normal operator combinator will return in the current operator as a string and its expression every time. Okay, I'll see. Like I don't try. I need to play with this for a bit. We have a token parser, and then we can use parentheses, braces, identifier, reserved, and so on. Okay, but I think for this we kind of need to do something like we need to ignore like parsing the string type, right? Do we want to like or actually how do we even do this? Do we use this like where is it? Reserved? I think so. I think that's the thing to do here. I need to do something like, where's the example here? This thing, right? So we need to use this. Yeah, because this then takes care of spaces and all of the like other annoying things and parentheses and so on,
Okay.
right? So you don't have to worry about this. I think this is in token, and then instead of
Token.
this LC def. Okay, and then I guess we don't even need to do the other. Like we can do the we can just do p here instead, and we can do p dots reserved, I guess, right? And then we can do even this because the result is a unit, if I saw it correctly. Yeah, probably I'll do that after I implement this. Okay, so we that's how we get a like the keyword there, and then we need like an identifier, I guess. But then how does identifier work? Did we explain it here? Identifier start is a letter, and then it's alphanumeric and this, and then maybe this. Do we care to force types to be uppercase and names to be lowercase or no?
Yeah. Let's do this.
Okay. I guess we can do it customly here inside our own thing, right? So we can do name is p dot ident start. Well, no, it should be an identifier or something, right? So angles, braces, brackets, literal colon, comma. You can use identifier. Where is identifier? Okay, here we go, identifier. And then we can do guard. Where is guard? Sure. And we just need the first letter to be uppercase, right?
Yeah.
Wait, and is this what type is identifier? It's a string. Okay, so what's the function which takes the first convert string on safe throws? Okay, not this. From string. Yeah, so identifiers, okay, reserved should make sure that type is the first thing here, right? So we're parsing, oops. Where is it?
Show the example again.
Yeah, here, right? So it's going to parse this, right? And then like identifier should parse the next thing, right? Which we assume is an identifier. And then guard will fail the parser unless, and then I have to write the condition here, right? The condition here should be like something like the first thing, like first letter in name is uppercase. The problem is that in PureScript, strings are not list of characters, as in Haskell. So I need to find the function which gives me like the firsts. I wonder if there even is one. I don't think there is. I think we need to do the...
You want to take the first letter?
Yeah. I think there's something like in code point or something, which definitely does that. This is always something that I never... Okay, it's a... Who even knows? String... Hello. Not byte strings. No, it's not.
It's not a list.
It's not there because it's not a list. String, strings extra, string utils. There's one of the string libraries which has that sort of module in it. It's not this. Yeah, I think this is the one. Yeah, PureScript strings. This has to be it. Okay, so maybe there's something inside char, but I don't think so. Nope, not that lucky. And I don't think it's here either. Uncons. And we can look at head, which is a code point. I was hoping it would work with chars. Last index. You can take one. Just use regex. No. I refuse. Drop count contains. Okay, maybe I don't want code. Okay, so these are parts for. Wait, what's code units? Programming is hard. Okay, singleton returns a string of length 1. No. From char array to char array. I guess this is what we can do, or we can get char at, but that gives us a maybe, which is fine because you can fail it if it doesn't exist, right? So we can use this. Unless there's a uncon. Oh, here it is, uncons. I guess this is what we want. Does something like this Pascal case exists? There's a head for strings in PureScript yarn. Yeah, I'm not gonna include that. Yeah, maybe we can also look for something like case, but this converts it, right? So, and I don't think it searches for, yeah. So let's see. No, I don't think there is. Okay, so we need to include strings.
Yeah.
Sure, I could do that.
It looks like a card.
Hmm?
It looks like a card.
Okay, install actually. Yeah, but like, is there a Pascal case somewhere? Because,
Hey, it was there.
but it's in. Yeah, I still need to include an extra library, right? Regardless, but I guess it's easier to use this. I guess so.
But wait, the Pascal case will delete. Oh, okay.
Is it strings extra? Yeah.
So we want we want to delete also the white space.
Well, no, like that also does like the
Will solve the problem.
no, what's it called? The Lexer that we're using takes care of spaces. I'm pretty sure. I don't think we need to do anything about that.
Okay.
I don't think we need to worry about spaces. That's the whole thing of using the. It does that by default. So I guess we need name equals to extra dot Pascal case of name. I think that's reasonable. Okay, so now we have a name, and then okay, let's open our alt LC thing here. So then, okay, if we have a type, then what's the result? Well, so we want to do a type, right? Not an AST. So I guess it's just type and symbol, right? Use my joke solution. Actually, I think that's nicer because otherwise you have to do maybe, like leave the maybe to parser T or whatever. So I think that's actually better than what I had in mind. Okay, so here we just need to do pure and then use what? It's just type and then symbol name. I think we need to import symbol from our own thing. I think this is correct. I guess we should test it, right?
Yep.
So if we just comment these lines,
Yeah.
then it should work. Well, no, it won't. We need to literally just pass it this, right? Because we're not telling it, like we have a type parser. We're not telling it how to do, what to do with anything else. So yeah, I think we need to, like, okay, let's try starting a REPL. What is called lambda something. PSCI. Oh no, okay, it's this. Spargo REPL. Okay. And we need to load our. I have not used the PureScript REPL in so long. Maybe we should have written a test instead and then just ran the tests. Because that way we can keep running them later and not break things. Okay, let's run it like so, and then we can copy it to the test. Yeah, no, I'm not complaining about the compile times. It's just that it's better to have them. Okay, so we can do, I think, import, and then we do lambda dot types, I guess, was syntax, and then parser. Okay, then how do we run the parser now? why do I have so many tabs open? So it's what package is this? It's parsing. Guess it's here. Run parser. Okay. So we can. Okay, we also need to import this, I guess, right? So we need to import this. Okay. Run parser. Too slow. Type. Well, what was the type again for run? I guess we can just look here. Okay, so the first argument is the string, right? So we can do type A as the first example, and then this is the parser, and let's see what happens. Ooh, what? Oh, we don't have a show instance. That's a very reasonable error message. Give me 1 second. Syntax, yeah. So we need to derive. Ooh, and we don't actually, like, you can't derive show, right? Oh yeah, to convert it to the wrong. Yeah. So Pascal doesn't work. We need to change that. Okay, so how do we do the generic deriving in PureScript again? Turns out that this part would have been easier in Haskell.
Logic is way more easier.
Oh yeah, like just derive generic. Yeah, but don't I need generic rep? So I guess I need to like derive instance. Yeah, I need the library. It's just generic rep, right? Like so. Can we go over to the tablet?
Yeah, exactly.
Okay. I guess I already had it as a like transitive dependency, so it would probably have worked anyway. Okay, so deriving instance. I have to give it a name, right? So generic type. Oh, and then I have to do it for everything. So I have to do it for this thing. Why doesn't it autocomplete? Generic type. Hey Vlad, you gotta create string operation Thursdays when you just make a proper string library. Wait, so isn't it called generic? Why isn't it finding it? Oops. Generic, it's in. I mean, there it definitely exists here. Oh, okay. Is it like it's like this, right? No, it was correct. I'm like crazy. Oh, okay, just did install. Okay, it's also to do build. Oh, I see why. Okay, so let's see. Hello, can I get the error now? Can I get the import? Okay, thank you. So instance has been defined okay, it has a different name. So this is for symbol. Hello, can you go away? Okay, so this is for symbol. Okay, and this is for term. Actually, let's also define show instances. Well, actually, we can just use new type instance show symbol. Show symbol. I think this works because it's a new type. Well, derive new type instance, I guess. Okay, and then I need to import show from somewhere. Wait, we don't have prelude here. I think show is in prelude, right? There we go.
No.
Okay, so how come the need to generics? I'm being a person that knows nothing.
I am the person that knows nothing.
So because PureScript doesn't have cannot derive generic like show like Haskell has. Right?
Okay.
Haskell, the Haskell compiler knows about show and it's able to derive it. The PureScript compiler can only derive functor, EQ, ord, and like a couple of more also generics, but not show. So we need, but it knows generic, so then you can do generic show. Yeah, it looks ugly, but we'll use PureScript Dodo for that for pretty printing, Nate's library, but not now.
Okay.
We won't worry about it. We just want to see if the parser is correct. We don't care if the printing instance for our AST looks right. It looks cool. We just want it to be correct. So I guess we need to do instance show type show equals to generic show. I think we need to do this, although I think we need to do something. Okay, we need a where here. I think we might, no, that's all we have to do. Okay. Generic term. Term. I think that's also done, and now we don't even need one for AST, but we'll need it soon enough anyway, so okay, that should be good. Okay, so now we need to reload everything. Okay, we need to restart the whole session. And then, oh, sorry about that. So we need to import syntax. We need to import parser. I was telling Denisa earlier that we'll be done in no time. Do you remember me saying that?
Prepare yourself to do sequence calculus, Didi. We will finish in half an hour.
Okay, so it parsed it correctly, right?
Hey.
And then we can do A, B, C, D, and this will work.
Wait, what happened there?
What do you mean? It's a type. And we get it right because it's an either, because the parsing can fail. Okay. Right, because if we have like this, then we'll get a left saying, okay, I expected type, but found something else.
Yeah,
right?
try this example, I think it will.
Yeah, I know, I was deliberately not trying that example, because this will fail.
Yeah.
Okay.
Let's change
syntax. Not syntax parser. Okay, so we actually do need to use the stupid head function, right? Head, which is, well, let's use string.head. Which of the stupid functions is it? No, it's unconst, I think. Wait, was there a head function that did this? I think I found some stupid function.
It was unconst.
Think it, okay, whatever, I don't even care anymore. Okay, so no, I think I want the char version, and this gives us a maybe. No, I think there was a head which returned a maybe tail or what, maybe what, I don't even care. No, I think I was looking at index or something. But I don't remember. Char at. Yeah, there we go. Char at was what I was wanting to use. Can make your own head. Oh, this is unsafe. I'm very tempted, but no.
No.
Char at name. Sorry, char at 0 name. Okay, so we want to use maybe over this thing, right? And okay, so if we find that character, we want to make sure that it's uppercase, right? Yep. So I guess even ASCII uppercase, right? Because we need it to be literally a letter.
Yeah.
So char. Okay, and then otherwise, well, wait, what's this? Yeah, we need it to be false, right? So we need for as a default, we need it to be false, right? And if it's not false, then I need it to be uppercase. And it can still be false under those circumstances.
Let's check again.
Okay, so let's see if reload works now. Okay.
Yay.
Right, so now it just keeps our name, however you capitalize it.
Yay, we have time.
Cool. So we did 0.0001% of our parser. Okay, let's do like tokenizer, or how should we call this? I guess let's just call it parser. And what type is this? Oof, are you serious? Is there no type for this? What's the name for the function again? Let's make token parser. Okay, it's gen token parser. Okay. Gen token parser for string and identity, I guess. Okay, and then we can remove this and then use parser dot, and okay, they should still be the same thing if I was able to type correctly. Okay, cool. Let's move this to the bottom because this is just like implementation detail. Okay, so we can parse types now. So now let's think about parsing terms, right? And the way we'll do it, we will create a function for each of these separately, and then we'll just like, oh, stick it in a test. Yeah, fair enough. And we'll move this function later, but oh, sorry. Okay, so let's see. Here we want to do something like we love tests. Actually, we'll need a testing framework, but we will not bother with that right now. We'll just like do some prints if it fails or something, right? So okay, we need to like get our parser. So that's something like let parser equals to run. Well, no, the parser is just test, right? So we can do run parser. Yep, test. Hello. Oh, no, it's type. Oh, sorry. Type over some values, right? Okay. Yeah, I guess we need to do something like a helper, right? So we'll assert we need to take some like string, and then what type is this? Parser type, and then so I guess we'll just assume that we'll just assume, and I guess the other way is way more. Okay. Okay, so we can do something like case this of left, and we don't, well, I guess if we get, I guess we want to see the error, right? If we have an error, then log and otherwise you don't care, right? And then we can do something like if it fails, and then the parser is test, and then we can write type A here, and then BC here, and then I mean, it doesn't even matter because we're not even testing the output. We're just making sure that things work. And it's not test, it's type. Then we can figure out some better. Oh, this is not the correct parser type. Well, we can import the one we use there, I guess. And then we can import left and variable A. Okay, this is not Haskell. Could not match string with. Okay, I think this has the different order. This works like this, and then we need 2 spaces here. Oh, so parser error. So does it have a show instance? Please say it does. Okay, cool. Okay, so we wrote some tests. We're never going to run them, but we wrote them. Okay, cool. So let's figure out. So let's do variable, right? So we also have to do the type parser, but let's do variable first. Then you'll feel good. I mean, sure. But then it just doesn't say oof, right? I guess we can make sure it works if we do. And then it should oof. Oops, I didn't want to close that. Oof. Yeah. I mean, it still says test succeeded, but at least we get the oof here, so we'll know it failed. Okay, so we need to do a variable now. So variable is a parser for a term, right? We're starting to do term. So variable is, what should we do here? Well, so there's no reserved term here, right? It's just a identifier, I guess, right? It's just an identifier as a name. We
have a guard. It should be small.
So we want to do the reverse, right? We want to do the guard thing. Okay, so we just copy this here and then just do is ASCII lower, I guess, and that's all we need to do, right? And then what? Pure term. Oh no, variable symbol. Wow.
Okay.
There we go. Okay, we also need to import this. You have no idea how good it is now. Like in Haskell, maybe 1 month ago or 2. Hello LVC disk. You had to do the imports manually, right? So you have to look. I need variable from wherever, and you have to go here and type. Okay, import this from variable. In Haskell now it also works, but it's PureScript. This has been working in PureScript for like at least 2 years or something, right? Wow. So even though it has a way smaller community, that nice. Barely now is the Haskell tooling almost has places where it's better because it can generate stuff now, right? Like Sandy and Reed are working on that. But yeah, that's surprising. Haskell has been there for like 30 years or something, and there's like so many more people using it. We had our work cut out. We've all had to take a pay cut of the time because of the time we say. Yeah, it was so bad. Dealing with imports was so annoying, and it's even a lot better in PureScript than it was a few years ago. So they're improving a lot. So should we add tests now for this?
Sure.
So we want to do what? So variable, and we just need to do like variable names, right? And then let's make sure these two pass, and then. It's very bad. I'm from Russia. Don't worry about it. I think I forgot to remove this thing, which we knew failed. So yeah, we're using PureScript, which is a purely functional language, very similar to Haskell.
Should we get another wolf?
No, it's just to test it. Yeah. So let's do like this, right? And then we got the oof, right?
Wait, can you go back?
It doesn't, like, the error is terrible. It doesn't tell you where, why,
But
or
isn't
whatever.
this? Ah, no, it's another one.
What do you mean another one?
I mean, wait, shouldn't it? So it logs only one wolf or two?
No,
wolves?
but I removed the
okay.
type oof. Right?
Ah, okay. Sorry.
After we make sure that it works, we delete the wrong thing.
Okay,
right?
okay. Sorry,
Let me close this because I keep tabbing.
you were too fast.
Okay.
Okay.
So variable seems to be working. Singleton oof. Right. So now we need abstraction. Abstraction parser term.
Wait.
Okay. So what's this?
We have what reserve.
So we have a list of symbols, right?
Well, we have the slash.
Oh yeah, right. We have the slash. Okay.
And the point at the end. How you handle that?
What do you mean how? We just do slash and then the other things and then the point.
Okay.
I think there's like, let's see, because we need to look at the like things from here. Let's see if I'm able to find it faster than Yu-Gi-Oh will give the answer. So I need to look here, right? And we need to look for something like identifier, I guess, or no, it's not. It's reserved operator or something. I'm not sure. Like, let's see, what do we have here? I wasn't paying attention. So I guess, yeah, it's reserved operator, right? Yeah, I guess so, right? So we need to do something like p.reserved op. Is it op or operator? Op, okay, and then we say this, right? This means, okay, this has to be here, right?
Okay.
Okay, and then we have to parse as many, yeah.
Which should be variables, right?
No, because we said it's symbols. So maybe we need a symbol parser, right? Yeah, we need a symbol parser.
Can you show the symbol again?
It's just a, like, symbol is just
String?
a string. Yeah, well, I don't even have it here, but it's
Yeah,
just
but
a string.
Wait. But when you write the abstraction, you want to have there just to have variables, right? Or
Well, like, variable is a constructor for term, so then I cannot use variable here. The alternative would be to use term, which would be like, I don't want to be able to do any of this, right? So I kind of have to use symbols.
Okay.
This would probably work in a dependency type language where you could, like, everything is at the same level, but here there are different levels.
Okay, so you have to write quickly a parser.
Yeah, I mean, I kind of wrote it here, and then we'll just move it from here to here, right? Because, like, we will. I mean, I guess it's literally the same thing. It's just this, right? Except it returns just a symbol name, right? And then here, instead of doing this, we just do type over symbol. Yeah, right? We just added an extra constructor on top of it, like f mapping or mapping. Okay, so then we need to do many, I guess, which gives us an array, unfortunately, but I guess it would be what's even, it doesn't even matter. You can use, okay, let's see, what's sum? Non-empty sum. Is there one for non-empty? Because I have a non-empty list there.
But couldn't we put a non-empty array? What would be the difference?
We could use a non-empty array. Lists are slightly less annoying to work with. So yeah, I guess we can use a non-empty array instead anyway. Okay, so we could do some symbol, right? Yeah, I think that's actually correct. Oh, and then okay, but we need to change it in syntax, not in that file.
But also update it because we will forget.
Okay. Hello.
Delete the non-empty list.
Okay. Why would I need to do that? Like I can only do, I could just do this, like list is this, like identifiers, and then I could just do, give me 1 second. So I could do, okay, but I also need to get the term, no wait, then I need p reserve op this, right? Yeah. And then we need to parse a term, right? Well, let's do t. But we don't have a term parser right yet, so we can try writing it, right? So we have a term is either vary for now, and then we'll add the rest later, yeah. Right? But for now we can just do, okay, it's either that or that. Okay. Okay, yeah, I get it. Yeah, this is easier, right? So right now it's easier that we've chosen an array, or actually it's kind of the same. So we have a pure abstraction with identifiers and t. I think they should compile. Okay, but it's parser now. Okay, and then what's the problem here? Is undefined. What do you mean? Do I really need to do this? Oh, yeah.
Can you do this?
You need to use a fixed point operator. I forgot this is. So this isn't a problem in Haskell because it's.
Whoa.
Yeah, this green screen. It's fine. Right. So okay, this is a problem now because in like Haskell, since it's lazy, this is not a problem, right? But we need to. So how do you even do this actually? How do you use the fixed point operator here? Is there make abstraction take term as an argument? And so you're saying make abstraction take the term as an argument. So it's saying something like this, and then it doesn't. But no, like it should take this. Oh, so you mean like this? You mean? But then, like, I can't do this, right? But you mean here, right? Here is where I have to define it as fix. Fix. Also, it has to be inside lazy, so I need to like. I don't think parser is lazy, or is it lazy? Oh, it does. It is. Okay. I mean here. And then, of course, we need to. Yeah, I know. Okay, do we need this? I don't even remember. No, we don't. Okay. Okay, but that makes it awkward to test abstractions separately. I don't know. You can just pass it term, I guess. Well, I guess the thing that we could do is we could do this here. And now I could say, can't I say this? Well, no, because then, like if I try to define abstractions in terms of, yeah, then this will also need to be a fixed point anyway. Yeah, whatever. That works. As long as I don't use it inside term. So I can say this over term. Okay, that works. Okay, cool. Then we can test this one instead separately. Yeah, I get it. I get it because you don't create a circular dependency.
Okay, write a test.
I'm sure it's fine.
Well, for us. For the rest of us.
Okay, so okay, let's open because we've written quite a few things here, right?
And
Without
also
writing tests. So maybe okay, let's do something that's slightly smarter. So let's do traverse. Not the new type one, this one. Okay, so what was the type of traverse? Well, this traverse actually. So it takes the function first, which is this, and then let's do this.
okay.
Right, instead of this, we can just do the traverse. I'm pretty sure it should be the same thing. Yeah, this thing. Oops. This thing, right? Okay. Okay, so now it's easier to read them, right? So let's see. We need one for symbol, right?
Mm-hmm.
Which is kind of the same as variable.
Yeah.
Okay, you know what we should be doing here? Oof. On input. At least so we know which input failed, right?
Okay.
Okay. Then maybe let's use slightly different things, right? From here, let's say A, B, just so we know which one failed. Okay, so we have symbol, then we have variable, so abstraction. So this is kind of like, okay, lambda x dots, and then we can only parse variable. So this is the only thing we can write here, right?
Yeah.
We can write anywhere, anything, because we're not type checking, but we can only do this so far, right? So there's do x, y, z dots, whatever, doesn't even matter, right? What we put here.
Okay.
Okay, let's test this too, I guess, right? Unknown value symbol. Okay, I have not imported symbol. Hello? Hello, Mr. Okay, there we go. Okay, so we have error for a result or type. Wait, type.
Huh?
Wait, did this fail?
What happened? You broke it. What did you do?
I have no idea. Is it because of, oh, how? It doesn't reset state. Oh, you think it works on like the folder one instead of working on effect? Why would it keep the same internal state? Aren't there different parsers? Like, okay, let me comment this
Yeah,
out.
just keep one.
Okay, this works.
No, two of them.
Oops. Okay, so now it still works.
What happened?
It still works. It just got a warning that we're not using this. So I think we broke something with our type parser. Let's just look at type then. Yeah, so we broke the reserved word type. Okay, so how did we break our type parser? Oh, okay. Oh, right. Because this is obviously the wrong... We broke the type parser. Because it's not only that. We're not parsing the type word anymore. We're just typing like... we forgot this. P dots... what was it? What was it called?
When did you...
Because I thought, okay, this only parses that, but I forgot it also parses the... I guess it's reserved, right? Type. And then I think that's... Yeah, we need to do that. And I think it works now. And it's parser. Is that a royal we? No alternative. Oh, okay. Right. So this is not a symbol. I broke everything. It's not a symbol because it needs to be ASCII. Come on. Upper. Okay.
But when did you delete that code?
We did it earlier. Okay, so it's not symbol. We need to do type of this. I thought I would do a very smart refactoring, but it was not as smart as I thought it was.
Good question.
Yeah, let me add the test. Pretty sure it fails. Yeah, because like it has to be a single one, right? You're parsing a single reserved type keyword, not multiple ones. Okay, this is wrong. Okay.
So we're good now?
Yep, everything is A-okay.
How far are we?
We got like a few minutes left and...
Okay, first of all, can you go back to the example file there and then just replace that non-empty... Yeah, thanks.
I knew you were going to say that.
Okay, let's do application and then... Right, at least we...
Plus we can do lambdas.
Yeah.
Well, I mean, we know we're going to be needing this.
Call it application, yeah.
And we don't need two, right? Because we'll be using the same one in both cases for sure.
Okay.
Okay, so we need to do what? I mean, we need two symbols, two variables rather, right?
Yeah, and that's it, right?
I mean, okay. Wait.
Wait, what are you doing?
Why do we need the term parser? Because we know it's... Oh, no. Okay, we don't know it's variables. It's terms. Yeah, I think that's all we need to do. Yeah, no, my bad. It's terms, not variables.
You also want... Write a test.
Okay. Okay, so we have like, well, I mean, this is just this, right? This is a simple test. And then let's see, what if here we have a lambda, okay, lambda x dot x. And then we should probably force them to be parenthesized though, somehow. Because you can write this and it...
And you didn't mean that, right? You meant it.
I wonder if this works. No, because I think the previous one will greedily do this, so this will not work. So I actually think this might work. And I think the other one would fail, but let's see. Yeah, exactly. I think you're right, Yugi. And it will fail because it will not find the second term, right? Let's see these two if they work. Ooh, maximum stack call size exceeded.
What's that?
That's what you call bad.
What?
Where is it? Parser. So what kind of boo-boo did we do? Application can have application on the left, not without parentheses.
It looks like an infinite.
Oh, okay, I get it. Okay, so we need to manually say what can be here and just exclude application. Kind of like a left, which can be abstraction. I think we need to use this one. Or, well, the other one, right? Right, and then at some point we'll add the like parentheses thing, and then we can also have application on the left, but yeah, it won't work. So wait, do we have to manually parse? Yeah, that should work, but it will not allow us to do like, okay, I want to do, then I want for it to be interesting, because right now then, okay, the only thing we can do then okay, we can have abstraction. Okay, so then this would work, I guess. Expected what now? Oh, okay. Huh? Expected. I don't get it.
Did you save your file?
Oh, it doesn't understand the parentheses. Okay. But then, like, but this would work still? No, it won't, right? Because there's no way to separate between these two without parentheses. I mean, what would work would be, we could do something like, sorry. And I think this would parse correctly. Well, of course, if we write it like so.
Hi.
Hello, welcome. Yeah, like this parses correctly, right? Because then it's not a problem anymore. Right? So this parses correctly, but like the other way, we need parentheses for it. Okay, let's try add a test case for x, y. That will, okay, yeah. I think that should work. No, it won't. Can someone explain me why I haven't been following you? I'm not sure I can find a good answer to that, but thank you for the follow. Hello, Lost Algorithm.
Hi.
What's confusion? We'll make a parser real quick, then we can do the theory part. Well, okay, that was my bad. I did that, right? I said that this will be... yeah, I told her that will be done in like minutes with this parser thing.
At most half an hour.
Okay, so wait, did this work? How does it parse it? Oh.
But we can see how it's parsing. parsing it, right?
Sure. Why do you say that's the wrong way? That's the right way, actually. Oh, it should parse, but it parses fxy. Yeah, we're doing lambda calculus. Some like a typed lambda calculus, actually. Okay, so left can only be. Oh yeah, it cannot be application, so it parses it wrongly. Oh, you're right. Like even without parentheses, it parses it in a wrong way. Wait, is the bot dead now? The bot has died. Okay, I restarted it. It should be back in a minute or so. To demonstrate math. Yeah, but that will probably take a while. Right. I think this should work now. There we go. But like we have a longer term example.
Yeah, let's have a look at his
I think this is
yeah.
it, yeah. Token expression. You're welcome. So raw expression, atom. Search for with call. Here it is. Call unit. So these are just fixes. So I'm not seeing, where is this, the part that I'm looking at? So it have parents, where do you use parentheses? Oh, here, wrapped. Oh, okay, so it can be wrapped. Oh, so okay, this is a recursive function. Okay, so the thing is that, okay, so this is wrong because we need it to be left associative, right? Don't test me what works. I came up with that like 2 a.m. Okay, so we know we need application to be recursive or allow it to be left recursive. But wait, okay, see what the problem is.
It will take 10 minutes.
Okay, so what if we try to do it step by step instead? So the problem is if we run term parser now, we'll get into the infinite loop of starting application a billion times, right? And not ever finishing it. So we need to make some progress, which means we need to do to read something, right? So we need to like read some left, right? Something like the first term, right? But then we need so we have the first one, right? And then the thing is we need a second one, but then if there is a third one, we need to like do the correct kind of association, right? Is that the right way to think about it? I'm not sure. But okay, so we did some progress, right? We read some T. So now we can recursively call the term parser. But then, okay, so the problem is if we do that, then it will write associate. If we find another two terms, right? They'll be associated with each other. So we need to associate it with T instead of the, like, what's on the right.
Can we parse it from the other side? Can you parse it from right to left?
No, but I think we can do something like rest would be many term parser, and then we get like a lot of other terms, or as many as we can get. And then the next ones could also be application. We're fine with that, are we? No, there has to be anything other than application, I think. So it's literally just many left. So you just need to take as many as. What if there's less than 2? Then we fail, I guess. But then we need to go back.
You have some homework to do.
Embedded parsers.
Yep.
So imagine the term parser finds a non-empty array of atoms, where atom is everything but application, and then you could just fold over that to create the applications. They do the recursion, but this should be clearer. You can use some atom to get the array and then fold right or something. Sort of, but then inside, like left, like what if you have something like f? So this works for this, right? Where you do the like f, x, and then y, but like you can't really ignore. Like what if you have f? Like what if I literally write f, x, y, z or something, right? Kind of need to, you need to like look at parentheses differently, like allow bracers to recurse, but not like otherwise not allow other applications to happen. So you kind of need something like you need a term parser which doesn't include, exactly, which don't think, but like, but whatever is inside bracers need to be the whole term thing, right? Which includes application. So okay, let's call this atom because I like that word. And then we can get many of these. And then I guess, we can just, but what if we have only one? We just fail? No, we should just go to the next thing. So we need to backtrack or something if this fails, right? That's the problem, right? What if this fails? Like what if this only... I mean, if you try application last, that's fine, because... we need to go, right?
Yeah. Or at least I have to go. I have to check the baby.
No, I think we need to stop now because
this will be your homework. You have to fix this.
Oh,
and then we can do
fix it off stream?
I don't know. Let's ask them. But then...
I mean, I can fix this off stream and then show how I fixed it.
Yeah, and then we can move
and
to
then
the
we can...
part.
Oh, you mean the whole parser? What do you guys think? Do you would you like me to continue the parser on stream or off stream? Okay, so let me explain. This, like, the hard part with the logics and everything will be happen once a week, right? So
Okay,
it will be next week.
maybe we can say again what's the goal, because...
I vote for parser on stream.
Okay.
Okay, so then I have no idea what else you do on stream,
exactly.
but this is fun. Okay, so let me explain because there's a
I'm
few new people. And who's Didi? So this is Didi, this is Vlad. Let's do a small explanation for the new folks. Okay, so I do daily streams. I start every day, and he's Dexter. Nope. So okay, I stream every day starting at 1 p.m. GMT, so roughly 2 hours earlier than now, and I do just Haskell and PureScript. And now every Tuesdays, which is today, and then next Tuesday, and so on.
This is the first Tuesday.
But this is the first episode of this. We'll do Type Theory Tuesday with Didi, which is Didi here, right? So I guess next week is when we'll continue at least the like complicated part of this.
Okay, but let's.
I might work on the parser because I don't think that's too interesting for you.
I am interested, but maybe just fix this problem, or I don't know. We can go over the code anyway.
Yeah, we'll see. Yeah, we'll see.
So the
but
main
then
idea.
the whole idea is to. Okay, so the end goal next week we invent Mandark. Yeah, but I'm not Dexter though, so. Anyway, so the whole idea is we'll write a simple language, which like a simple type language that calculus that obviously has types, right? It's simply typed.
The idea is to after that to use theory, to use logic, and use math in order to write the implementations or write some implementations for a function you would write in this simple calculus, right? In this simple language.
So this is kind of like the thing that if you've been following Haskell, you would have seen probably the Haskell language server that has something like this. Although that's not always guaranteed to work, I don't think, because it's mostly heuristic, I think. Whereas
and we want to use sequent calculus in order to find a proof for a certain formula and use it and move it towards natural deduction and back to type theory, so we solve this problem.
But like the basic idea is you write a like type, and then you get the implementation for free.
Yep.
That's the basic idea.
Which behind doesn't have an heuristic, just have an.
Which behind is literally a logical proof,
which
is like an algorithm to find logical proofs.
Yep.
And this works for STLC. We know it works for STLC.
Yeah.
And we'll see if we can, like, after we've done this part, which will take a few weeks for sure.
After today,
judging by today's standard, it will take forever. But
because Vlad was this morning, okay, this will take 10 minutes. Prepare your second calculus. We will do it in just like this. So,
Turns out that I'm not familiar with these libraries though. Like in Haskell, it would have been faster. But I want to get familiar with them. So
done.
And also, it's cool because we can use this, like, since it's PureScript, we can compile it to like in a web page, and then maybe your students could use it online or whatever. So that's one of the reasons we're using PureScript. So next week. So what I will not do until next week is I will not do the small step semantics.
Yes,
let's do that together because you like that, right? That's
sure,
cool.
Sure.
So at worst, I'll just finish the parser and then explain it.
Yeah,
and if not, we can just continue the parser next week. We'll see.
We will see.
But the longer term plan is, but Haskell cannot. No, it can't. I know it can, but no, it can't. Right, but so anyway, next week we'll do we'll continue. Okay, but the long term plan is we'll complicate this STLC, and we'll see what happens if we add recursion. Can we still write the algorithm that works? What if we add whatever, right? So we'll try to complicate as much as we possibly can, Haskell can do this in one line. I don't think so. New show installing JSC.js Fridays. No, not gonna do. I just don't do JSC.js. No. Anyway, thank you very much for joining, for following. I actually don't know Rust. I need to learn Rust at some point, but I've never, I've heard a lot of good things about Rust. I've never used it. I have to play with Rust at some point, but I have way too many projects right now. So we'll finish some of the.
What's it say?
I think lambda calculus, but I'm not sure what's a binary lambda calculus.
What's the binary lambda calculus?
I'm not sure. I'm not sure if that's what he means by binary LC, whether that's a lambda calculus. Anyway. Oh, binary encoding. Okay. Yeah, I don't know about that. Anyway, thank you very much for watching. Thanks. And I'll see you guys tomorrow. We'll do Haskell tomorrow. We'll work on our on our Haskell bot, Twitch bot. We have some cool things to do. Anyway, thank you
And
for
I'll see you next week.
thank you for
Thank you.
joining, and I'll see you.
See you. Bye.
Bye.